Welcome, everybody. We have made it to 2.3, where at this video, this lesson, you have earned the shortcut to the derivative, or the shorthand derivative. Oh, thank goodness, no more difference quotient. Life is going to be great from now on, okay? All right, so the derivative. We've seen the notation before. If y equals f of x, then f prime of x, y prime, d over dx, and dy over dx all represent the derivative of f at x. All right, so those are all notations for the derivative. Okay, so first rule is the derivative of a constant function. If f of x equals c, then the derivative of the constant c is 0. So basically, the derivative of a constant is 0. Nothing else to it. So remember what a constant is. A constant is a number without a variable. Okay, so looking at example 1, we have y equals -5. Let's find the derivative of -5. And we will say y prime, the derivative, since -5 is a constant, the derivative of -5 is 0. Okay. 2, same thing. Y equals pi. Pi is a number. Pi is a constant. So this means that the derivative of pi, since pi is just a number, since pi is just a constant, the derivative of pi is 0. Okay, but let's put into perspective what we just found. Because remember, derivative is just a fancy word for slope, right? Derivative is just a fancy word for slope. So let's look at the first equation, y equals -5. Y equals -5. Y equals -5 is the graph of a horizontal line, right? Which means that here is my graph y equals -5. Well, what is the slope for any horizontal line? And you guessed it, you took the derivative and found it. The derivative of any horizontal line is always 0. So the slope of a horizontal line is 0, which makes sense that the derivative of a constant is also 0. Connections, right? Easy connections. Okay, perfect. Next rule for derivatives is the rule that will be your best friend throughout the rest of the class. This is the power rule for derivatives, right? The derivative of a power function. If f of x equals x to the n, where n is a real number, then the derivative of x to the n is n times x to the n minus 1. So all we do is we take the power, we bring it down, and we subtract 1 from the original power that was there. Of course, I will go over with you on the next examples, but power rule for derivatives, that is your new best friend. That's what we're going to do. Okay, and then also take into account that the derivative of x is 1, right? The derivative of x is 1. Okay, perfect. Let's go ahead and find the derivatives of the following power functions. Okay, we'll go through all the notations as well, just so we get used to them and we see them. First step is f of x equals x to the fifth? Well, the derivative, which is going to be, the notation will be f prime of x. The derivative of x to the fifth is going to be 5x. The 5 comes down. We take 1 away from the original power, and our derivative is going to be 5x to the fourth. Oh my goodness, life is good, right? No more definition. We just did that derivative in like 1 second. Imagine if you were doing the definition on this problem. You would have x plus h to the fifth, which means you would have to distribute that 5 times. Ooh, maybe it's fun, maybe it'll build character, but now we're done with that life. This new power rule is great. All right, and that was it, right? That's power rule. That's shorthand derivative. You have now earned it. Maybe. 4, y equals x to the 30th. Like I said, let's play around with notation. So the derivative we will notate as dy over dx, the derivative of y with respect to x. You get x to the 30th. The derivative of x to the 30th is 30x to the 29th. That's it. Now imagine doing the definition on that one. That would be x plus h to the 30th. 30th, you would have to distribute 30 times. Oh, man. Our parents were like, we used to do that back in the day when we used to walk to school in the snow. Yeah, we used to distribute x to the 30th times. No. But that is good punishment for my kid growing up. All right. 5, y equals 1 over x cubed. Okay, before we take the derivative, we must rewrite this because we do not know how to take the derivative in this form yet. So we are going to manipulate it using algebraic properties. See, algebra is still a part of all of this. So we're going to use the negative exponent rule. Remember that 1 over x to the n can be rewritten as x to the negative n, which means we can rewrite this as x to the negative 3. And now we can find the derivative, which, playing around with notation again, we'll say y prime is equal to, and now using the power rule, the negative 3 will come down. You'll take 1 away. Be very careful with your math. You take 1 away from negative 3, you'll get negative 4. Okay. And now we want to rewrite this using that negative exponent rule again, because we want to be proper. Leave it in this form, you're a business major. Rewrite it, you're a calculus major. So this becomes negative 3 over x to the 4th. Done. Okay, let's keep moving. I told you, life is great now, right? All right, 6 says d over dx of x to the 5/3. This notation just says take the derivative of x with respect to x. Yeah. Okay, so same rule, power rule. You'll get 5/3 x. And since it's a fraction, right, maybe we'll go through this really quick. You will subtract 1, which means you change 1 into a fraction, get a common denominator of 3, and that'll give you 5/3 minus 3/3, which gives us 2/3. So our derivative ends up being 5/3 x to the 2/3. That's it. Seven, d over dx of the square root of x. Okay, well, we can't take the derivative in this form, so we must rewrite algebraically again. So another algebraic property. Remember that well, what could I say? Oh yeah, I could say the nth root of x can be rewritten as x to the 1 over n. Since this is the square root of x, this can be rewritten as, first, d over dx of x to the what power? The square root of x is the same as x to the, whoops, 1/2. And now, we put it in the proper form so we can take the derivative using the most popular rule for derivatives, power rule. We take the derivative using power rule, and we will get 1/2. The 1/2 comes down. You subtract 1 from the original power, and you'll get 1/2 x to the 1/2 minus 1 to the negative 1/2. Okay, we must rewrite though. We don't want to leave it like that. So we bring in the negative exponent rule, and this becomes 1 over 2x to the positive 1/2. And one more rewrite. So we're going to do the rational exponent rule. So x to the 1/2 can now be rewritten as 1 over 2 square root x. There it is. Beautiful. Algebra, algebra, algebra. Little bit of calculus, okay? All right. All right. Next rule is the constant multiple property. Okay. So this says if you have a coefficient in front of your function, take the coefficient, move it to the side, take the derivative, and multiply that coefficient back in. It's just the same as we did for limits, right? Remember, for limits, if you have the limit as x approaches some number of 5x squared, you can take that 5 and move it to the front. You can make it 5 times the limit of x squared. So we can do the same with derivatives. We can take that coefficient and move it to the front. Okay. You see, there's all these connections here, right? All these connections. So number 8. Let's use that constant. Let's try out that constant multiple property, which means this says d over dx, take the derivative of 3x to the 4th. So if I rewrite this, we can make this 3 times d over dx of x to the fourth. And now we take the derivative of x to the fourth using the power rule, and you'll get 3 times 4x to the third, which gives us 12x cubed. Now the question here is, do we always have to pull that number out in front and bring it in later? No. We can go ahead and just take the derivative straight on. If we started back at this first term, at the beginning, this 4 comes down and multiplies the 3, which gives us 12. Take 1 away from the 4, that gives us 3. We get 12x cubed without having to move that coefficient out. But the constant multiple property is there to let you know that you can move things around if you need to. Do we have to use it? No, not anymore. Now that you know the secret, okay? So, keep going. D over dx of negative x. Okay. Let's go back a little bit. Rewind right here. The derivative of x is always 1. So this means that for the next problem, the derivative of negative x should be -1. Fast forward. So there we go. D over dx of negative x is just -1. That's it. And maybe the question now is, why is the derivative of x 1? Why is it 1? Well, let's find out. D over dx of x. What power, what degree, what exponent is on this x but not shown? That is 1. Now let's apply the power rule. You'll get the 1 that comes down times x to the 1 minus 1. We take 1 away. So those don't look like absolute values. We'll make those 1s. This ends up becoming 1 times x to the 0th power. Well, what is anything raised to the 0th power? If you just said 0, please exit the video now. And yeah, just leave. So anything to the 0th power is always 1, no matter what. Anything to the 0th is 1. So this becomes 1 times 1, which is 1. This is why the derivative of x is always 1. The derivative of negative x is -1. Makes sense now, right? There you go. Little proof. Okay, next property for derivatives. It says you can apply derivatives over the sum and difference of multiple terms, just like limits. D over dx of f of x plus or minus g of x is the same as d over d of x of f of x plus or minus d over dx of g of x. So we can apply the derivative to multiple terms, which is what we're going to do in number 4. Example 4. So we should be veterans by now of the power rule. So let's just go ahead and take the derivative of this expression head on. No moving a constant or coefficient out. Let's just do it. So Let's start with the derivative of x to the 8th. The derivative of x to the 8th is 8x to the 7th. Let's then do the derivative of 12x to the 5th. The 5 comes down, multiplies the 12. 5 times 12 is 60. Take 1 away, 60x to the 4th. Let's take the derivative of negative 4x to the 4th. Same thing. This 4 multiplies that 4. Negative 16x, take 1 away, 3. Plus, let's do it again. Derivative of 10x cubed. 3 comes and multiplies the 10. 30x, take 1 away, 30x squared minus the derivative of negative 6x. Well, what's the derivative of x? The derivative of x is 1. 6 times 1, 6. And what is the derivative of 5? 5 is a constant, so the derivative of 5 is 0. Done. See, that was it. You're probably thinking derivatives are easy. They are. Okay, perfect. Let's move on. All right, looking for horizontal tangent lines. Find the points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. Okay, well, we saw it earlier. If you have a horizontal line, whether it be a tangent line or just a regular horizontal line, the slope of a horizontal line is 0. So in order to locate where a horizontal tangent line is, you're going to take the derivative, set it equal to 0, and solve for x. Simple as that. So that's what we're going to do. So let's take the derivative of the function above, and I'll just say y prime. Y prime, the derivative, and the derivative of x to the 4th is 4x cubed. The derivative of 6x squared is negative 12x, and the derivative of 4 is 0. So now, what we're going to do is take our derivative, y prime, and set it equal to 0, because a horizontal tangent line has a slope of 0, and the derivative represents the slope, so we want to find the x values where the slope is 0. So we take our derivative, (4x cubed minus 12x), and solve for x. Now back to algebra. We see there's a common factor of 4x, which leaves me with x squared minus 3 equal to 0. Set these equal to 0, and you'll get x equals 0 and x equals plus or minus the square root of 3. At these x values, a horizontal tangent will exist. Okay, so this is almost done because it says find the points, right? Find the points. So the next step is to take these x values and plug them back into the original function. The original function. So that's what we're going to do. Find the points. So take them, plug them back into the original function. So at x equals 0, and I'm going to use a calculator. Well, if I plug in 0, y is 4. And if I plug in the square root of 3, now I'll use a calculator. X to the 4th minus 6x squared plus 4 square root of 3. I get negative 5. And negative square root of 3, I should get the same thing. Negative 5. Okay, and it said points. So this makes 0, 4, square root of 3, negative 5, negative square root of 3, negative 5. Okay. These are the points where a horizontal tangent line will appear. Now, what does it all mean? You don't have to draw a graph for this one, but I want a graphical representation other than, again, us just crunching numbers. So, if I were to graph this, well, let's say I have negative square root of 3 here, 0, and square root of 3. And then 1, 2, 3, 4, 5, there's negative 5. Now, look at the original function, x to the 4th. If you remember sketching these type of polynomial functions, which you probably don't, but it's okay, we think of the characteristics of it. It's just a sketch. X to the 4th, that is a positive leading term with an even degree. And a positive leading term with an even degree will always open up. Both tails will open up. Now, we know we have points where vertical tangents exist, so let's plot those points first. So I have a point at negative 3, negative square root of 3, negative 5, 0, 4, oops, didn't do that, 1, 2, 3, 4, 0, 4, and square root of 3, negative 5. Okay, where all I have to do now is, since my tails open up, I will come down from infinity, hit this point, bounce off, hit that point, bounce off, hit that point, bounce off, and go. Okay, so what we're saying is that at these points, a horizontal tangent line comes in, shares that point, and takes off. So this means I should have a horizontal tangent line here, here, and here, where these horizontal tangent lines have a slope of 0. M is 0. M is 0. M is 0. And that's what we found. We found the location of where these horizontal tangent lines exist. That's it. Very important concept when we get into curve sketching. That's after the second test. Okay, next is the derivatives of sine and cosine. Keep these in your head too. Look at this. The derivative of sine is cosine. The derivative of cosine, negative sine. Okay, let's use those to find the derivatives of the next equations. All right. So 11, y equals 3 sine theta plus 4 cosine theta. Again, I'm going to play with notation. I'm going to say, not that, dy over d theta. This says, take the derivative of the function y with respect to theta. So, using our new derivatives above, we're going to get that the derivative of 3 sine theta is 3 cosine theta. The derivative of 4 cosine theta is going to be negative 4 sine theta. That's it. I can't believe my eyes, right? Too easy. It is. Definitely is. Yeah. Do it again. Z equals a over y to the 10th plus b cosine y. All right. So before we begin, we're gonna have to rewrite a over y to the 10th. And all we're gonna use is the negative exponent rule, meaning we're gonna take y to the 10th, flip it up. So we'll get z equals a times y to the negative 10. Oops. Plus b times cosine y. Okay, we are now ready for the derivative, and to play with notation again, I'm just gonna call this one z prime, z prime. Okay, and now let's take the derivative, and for the first one, it's power rule. And for this problem, see a and b as coefficients. They are coefficients. So you'll treat them as coefficients, which means that when you take the derivative, this negative 10 will multiply the a. So we will get negative 10a times y, take 1 away from 10, from negative 10, and you'll get negative 11. Then the derivative of b cosine y, again, b, just treat it as a coefficient. Only look at cosine. The derivative of cosine y is going to be negative sine y. So you're going to get negative b sine y. Negative b sine y. Okay. Now the only one we have to rewrite is this one because of the negative exponent. So our final answer is z prime is negative 10a over y to the 11th minus b sine y. Z prime. Okay. Oh my goodness, that's the last one. All right, y equals sine theta over 2 plus c over theta. So let's go ahead and rewrite this algebraically to make the derivative look nicer. So what I'm gonna do is rewrite this as y equals 1/2 sine theta plus c over theta. So theta is the variable here that we're going to take the derivative of. So we're going to use the negative exponent rule to rewrite this one. So c over theta is going to become c times theta to the negative 1. I just flipped the theta up using the negative exponent rule. Okay, We are now ready for the derivative, and a play on notation again. We'll say dy over d theta, the derivative of y with respect to theta. And the derivative of 1/2 sine theta, just take the derivative of sine. 1/2 is a coefficient. The derivative of sine is cosine. So you'll get 1/2 cosine theta. And then the derivative of c theta to the -1, c is the coefficient. So all we really look at is the derivative of theta to the -1. We power rule that, which means the -1 will come down and multiply the c. So you'll get negative c theta, take 1 from -1 to the -2. One final rewrite, and you'll get dy over d theta is equal to 1/2 cosine theta minus c over theta squared. And those are derivatives the short way. Life is way better now, right? Woof. So all you really have to take away from this is the power rule and the derivatives of sine and cosine. Those are important. And that's it. Done.